Just to make sure. Okay, hello. I know my video is not there yet. My video is coming, but let me just start with just trying to be falsely dramatic here. Can you guys hear me? Or yeah,
Yes,
can
we hear you.
Yes.
thank you. And I love the fact that you just vocally responded, so that took care of the "can I hear you" question. Thank you. All right, awesome. I know I mentioned I may have made a mistake. I mentioned last Monday that there's an exam that's going to happen. It's not this Monday. It's a week from this Monday. I still don't want it to become too big of a deal in our lives, but I know that now that I've mentioned it, I should mention more about it. You will get a practice exam that will answer a lot of questions about that exam. I don't have it for you yet today, but you will be getting it. I think I can promise. I'm a little hesitant to promise, but I think you'll be getting it by Friday. And again, the exam is not this Monday. It would be a week from this Monday. So we'll have plenty of time to talk about this practice exam and have solutions to it and all of that. And it'll be on the material that we've been doing so far. But anyway, we're going to keep just moving forward with the material. But this question I'm going to ask now, I'm really impressed with where everybody went, by the way, last class. You guys added 3 vectors together. It's a tedious job. Again, until you understand it, it's tedious and frustrating. Once you understand it, it's tedious and boring, maybe. So it's not fun for anybody to add 3 vectors together. It's so much not fun that people actually generally skip it early in their never actually sit down and do that exercise. And it costs them a lot later on. I think I'm really actually impressed that I really believe that this class can add 3 vectors together, which really means they can deal with vectors, which really will help us fly through a lot of material coming up, a 203 and 204 material. So where we're going to go with this today now, and it is a step forward really into the physics of all this, we're going to deal with velocity vectors now. Yeah, I'm going to tell you, I'm going to give you a problem in a minute, all of you, any of you. I'm going to give you a problem that is going to look just like the problem. Well, it'll look a lot like the problems of yesterday and the day before. I'm going to give you vectors, and your job is going to be to add them together. And I want you to trust yourselves that anything that you did to add vectors together yesterday was correct, or Monday, was correct and should be done again here. Only it's going to feel maybe not the case, because these are going to be velocity vectors and the meaning of them is different. What the physical implications of what we're doing are different. So there might be temptations to make up new rules or this or that. But anyway, if you really trust what we've done, then what we're about to do mechanically is the same, but scientifically, physically, will lead us to a much different territory. So that said, so basically, this is all still about adding vectors, but we're going to add velocity vectors today and see what that means. So I'm going to start with this question. So we're going to do it in parts as usual. So here's the givens. So please copy this down or whatever. Oh, sorry. And the reason I haven't put my video, sorry, for no reason other than that I really have to blow my nose. And but until I remember to do that, I'm not going to put my video up. So pardon me, I will put the video up in a second. Let me just write this down. I forgot I didn't have it. Okay, sorry. These are the givens. You might already be able to guess what I'm going to ask. You might not. I haven't asked it yet, but the givens of the situation, which we might even draw before I ask the question, the givens are there's two vectors here that represent something that's happening in life. Only now these vectors represent velocities. There's one velocity vector representing what you are doing on a sidewalk, traveling, let's say eastward. You are traveling eastward along the sidewalk by walking, and so we could say you have a horizontal velocity of 2 meters per second relative to the ground. First of all, we can assume that that velocity is constant, if you like, or we can just say, even if velocity is changing, we're just saying that we're analyzing one particular moment in your journey when you happen to be going 2 meters per second. Like it's an instantaneous velocity or it's a constant velocity. It's the only number that we're going to worry about in the problem. Oh, pardon me, someone's going in. So you're walking at 2 meters per second east relative to the ground. At the same time, but independently of that, rain is falling down, right? A different direction, not south, but down in the sky. And it's falling down at 5 meters per second relative to the ground, right? The speed of the rain is measured in reference frame of the ground, and your speed is measured in the reference frame of the ground. Now, if you remember the beginning of the year when things were abstract and we're talking about train of thought and talking about the earth and everything, you may want to remember from the back of your mind that all velocities are, you may want to put in the front of your mind that all velocities are relations, right? Like each one of these velocities that I'm giving here, the 2 and the 5, each one expresses a relationship between two objects. One is you and the ground, and the other relationship is the rain and the ground. But neither one of those numbers makes sense just on its own as a property of one object, right? Like the rain is going one speed. Every second, the rain is getting closer and closer to the ground, but it's but relative to the sun, it's doing something in a completely different number, right? And et cetera, et cetera. Where are we going with this problem? I'll tell you what I ultimately want to know with this situation. I want to tell you where this is going, but I want to honestly say in advance that what I ultimately want to know, I think is maybe too many steps to expect myself to figure out in one fell swoop. So I'm going to break this up into smaller questions as we usually do, but just so you know where this is going, what I ultimately want to know with those two facts is, that's my ultimate question. I'm going to break this up into steps for everybody, because I think it may be very possible that that's like the hard thing to get from all the way from zero. But this is the question: is at what angle should I tilt my umbrella? And I feel I'm going to walk away from the computer for a second. I'm going to blow my nose. Apologies, and I'm going to turn on my video and all that. I'm going to come back with like hint sub questions of this to help you get started if that's at all desired, assuming nothing has been said in the chat or anything at that time. But you can also feel free to just start now, because this is where we're going. You could do whatever you want to, like think about vectors, think about velocity vectors, think about arrows, right triangles. You might in fact have a very good guess as to how to set this up. It may be a correct guess. So I'll take anything, but I'll step back in a moment and I'll start setting this up. But that's the question. Okay, so I think that, okay, that's good. Do I see you guys? Okay. 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 Okay, one thing I'm just saying again, so the goal here is to figure out how I should hold an umbrella to stay dry. So I'm walking in the rain. Um, uh, and what we're trying, velocity is a vector quantity, just like displacement is a vector quantity. It has magnitude and direction. So it can be depicted, or we like to depict it with an arrow. And we believe that if we put the arrows carefully on the page, we can put them together in certain ways and compute with these arrows, right? Like just like we could add displacement vectors, we believe we can add velocity vectors by placing them appropriately on the page. Now, here are my two vectors, right? I mean, one's going to the east and one's going down. Before I go any further, let me just note that since, remember, you do positive and negative independently for each axis. Like each axis has its own positive and negative designation, right? So I'm going to make east positive because we often do, and because the dude, you in this problem is moving east. But I'm also going to make down positive. Like in terms of the up-down axis, I'm going to make down positive, not up, because nothing is happening up in this problem. There's no need for me to have like needless negative signs. So just to be clear, like, and it's not a contradiction, right? We make our own decision on each axis. So I'm saying down is positive, anything that goes down, and anything that goes to the east is positive, and maybe there'll be no negative numbers in my calculation. That would be just dandy with me. Okay, so that's what we have so far. So we have these two vectors, right? And then I'm asking something about an angle. Well, of course, many of you might be thinking, well, put these things together into a right triangle, and then he's looking for one of the angles in the right triangle. And that's totally right. Like if you're thinking you're going to put these two together in a right triangle and like get the hypotenuse, and then if you're thinking that one of the two angles in that right triangle is probably the one I'm asking for, the one I'm looking for, you're right. And you should do that and stuff. But the only caution I want to say to everybody, and I'm not going to do it yet. I mean, I will do it, but I think you guys can do it. I am looking for the angle in the right triangle formed by these two vectors, but I'm also looking for it to make sense. I'm looking for a way to hook up this material with what we've been doing the last 2 days. I want to put these two vectors together into a triangle, and they are vectors. They have tips and tails. So when I put them in a triangle, the whole tip to tail addition thing is going to still hold true. So I want to put, so we're looking for a triangle. Anybody can put anything in the chat or say anything they want. And if they say something about an angle or a sine or cosine, I'm sure it's going to be right, and I'm going to run with it. But I also want to be saying to everybody, let's not just randomly do math. Let's see if we can know, in other words, how are we going to choose which angle it is that I'm solving for? Why are we going to think it makes sense? Blah, blah, blah. I want to try to think of that while we do this. But I am looking for an angle, and I will shut up.
Professor, I just wanted to clarify on something. So I know you said that the person is walking 2 meters per second east and the rain is falling 5 meters per second south, but I missed the end of the problem, like the last page of notes. I forgot what you said the question was.
Oh, totally fair. Great. No, I'm glad actually you just made great. And not to be weird, but that totally counts for 50 points that you just did that. And that also reminds me to put these, but yes. Okay. So the question is to everybody, sorry, and I didn't say it clearly, you're right. What I ultimately want to know is if this situation is happening, if I'm walking down the road and the rain, I should say, by the way, it's not that the rain is falling south, it's that the rain is falling down, which I'm sure you know. I mean, but just to clarify to everybody, like on the paper, they look like the same thing, but I am actually saying this rain is like falling from the sky while I walk. The ultimate question to everybody, to Sarah, but to everybody, the ultimate question is, at what angle should I tilt my umbrella so that I stay dry? Or really, and there's an answer, or like, what's the minimum angle, you might say, so that I stay dry? And what's weird about this question is, of course, we all do this instinctively. Like, obviously, nobody needs physics to figure this. When you're walking, you just like hold your umbrella and you stay dry. But what this question really means to everybody is, what is it that our body must be figuring out automatically when we just tilt our umbrella until we stay dry? It lands at some angle. Like when you're walking, or especially if you're driving, you all know, like, I'm not going to get into it, but when you hold an umbrella, you might all notice you hold it at an angle, and the more the rain's coming down, or the faster you're running, you might have noticed, the more you tilt your umbrella, just instinctively, not with, oh, and we've got an answer in the chat. I'm going to shut up in a second. But what I'm trying to say to everybody is, what everybody bodily figures out by trial and error is they figure out with their body something that physics can explain. And that's what I'm asking here is like, what is that angle that's going on with your umbrella? And we have an answer in the chat. But yeah, sorry, but thank you, Sarah. That is the question. The question is, at what angle should we hold our umbrella if this is going on?
All right, thank you.
No, thank you. Okay. Oh wait, and someone's in me. Oh wait, and so yeah. Yeah. Oh, interesting. Yeah, oh, sorry. 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 I'm getting proud. So everybody think. I'll be with you in a moment. Right. Okay, I'm actually, yeah, people could keep thinking if, oh, wait, there's more. Okay, hold on one second. Okay, and I'll be with everybody. I would like, I am looking for an angle. I'm definitely getting some things in the private chat that are fascinating. Like I totally see why they're in the private chat. I'm trying to respond to them in the private chat, so bear with me. Again, no one has to use the private, I mean, no, but well, I am looking for an angle. I will tell all of you that there are already some of you in the room who are like, I think I know something to do, but it almost seems too easy or something. If you think you know something to do it. Even if you think it might be too easy or not what I'm looking for or not good enough, first of all, just do it because it's the thing in your mind, whoever you are. This is really major physics advice. It took me years and years to understand this, but if there's something in your mind at all, freaking do it, like on paper, because you will make progress. But second of all, this is one of those situations where if there's something you're thinking, but you think it might be too easy or it doesn't feel as right as usual, it probably is right, but there's a reason you don't feel like it's totally right. That's the thing I have to explain to everybody. But my explanation would mean nothing if you didn't try it on your own first and see. So do everybody, and bear with me for a second, because I also want to put the assignment portal thing in before I forget. Give me 1 second. But, and you know, many of you too, by the way, it doesn't harm at all, especially if you, this whole participation thing, you can literally put in the chat or in the private chat, you can put, I have an answer, and not even share what the answer is. And I would hope you wouldn't lie, but like even saying you have an answer, you've gotten somewhere, or like you've hit a wall, like saying I have an answer or saying I'm stuck. Like the thing, either saying I'm stuck, then I would follow up with like, okay, where are you stuck for sure? But if you have an answer, then that means you think you're done. And now you just want to find out, well, that's information to me. You don't have to confess your whole soul, in other words. But anyway, so everybody should try to get an answer. I'm looking for an angle. I've given you 2 sides of a triangle. At minimum, what you can do is just invent a right triangle and get angle, and just maybe it's wrong. But yeah. Right. What? And sorry. I'm falling. No, right. Well, since I'm looking for, okay, I'm giving you guys 2 sides, and I'm claiming they're, and they are perpendicular to each other, by the way. One is straight down and one is like across to the east. So I totally am giving the whole class 2 legs of a right triangle. So anybody who's thinking, can I do something with right triangles? Yes, absolutely. Now, does Pythagorean theorem apply? Yes, it does to any right triangle. Thing is, what am I asking? I'm asking for an angle. So if you should, if someone thinks in their mind Pythagorean theorem, this is compliment, not criticize. I'm just trying to watch your brain process and like, stay with you guys. The minute you think Pythagorean theorem, it's so helpful that you write it in the chat or you write it somewhere, because then it gives you something to try. And what you really should do is like write down a squared plus b squared equals c squared. And then you'll see, I've given you an A and I've given you a B, and you totally can solve for C. And that would be progress. The thing is, then you might notice what your brain is kind of already seeing when it says Pythagorean theorem. I'm not sure. If you actually write it out and do it, what you'll see is you totally have enough information to do it. You'll get an answer to the Pythagorean theorem, to C, and that will be right. But then you'll hopefully then look at the question and be like, oh, that's not what the question's asking. The question's asking for an angle. This didn't give me an angle. This gave me a side. Now, if you consciously write it out, then you'll see then just be like, oh, I got to do something to get the angle. What else can I do with right triangles? Oh, maybe like SOHCAHTOA, which is right. And then you'll do that. But honestly, the thing with all of us is what happens is the minute we think Pythagorean theorem, which might be right, we visualize starting to write it on the page just enough to know that it might not lead us to the question. We visualize it just enough to not be sure. So then we're stuck and don't know what to do. But if you actually write these things, I'm talking to everybody. I'm loving following this chat. And even though I wish it's always totally public, even when it's private, I'm just like revealing to all of you what I keep seeing in the private chat is the people that are doing the best for themselves are the people willing to commit to each next step, even just by writing it down in their own personal notebook. The trick of physics is every time you can envision any step at all in your mind, instead of questioning it, write it down first, then look at it to question it. And each time you write things, your questions will be you'll have much more confidence and you'll know whether you're getting there or not. The fact of the matter is Pythagorean theorem will totally get you the answer to not this question. And SOHCAHTOA will get you the answer to this question. And this is my last thing I'm going to say. But those of you who've already done it, and I know it's many of you because I see in the private chat, those of you who did SOHCAHTOA or SOHCAHTOA backwards or the inverse, blah, blah, and have gotten an angle, then you're intelligently, then those people are looking at it going, okay, I've got an angle. It wasn't that hard. He's looking for an angle. I've got an angle. He's looking for an angle. I've got an angle. But why the heck, how do I know if this is right? Like, it doesn't feel like it makes sense. I don't feel confident of this. And there's a reason. I'm going to explain to everybody why just looking at that angle does not make you immediately know whether to believe it or not. Because all we've done, if you've done this problem, and I will shut up, I keep saying that, I'm lying, but when we do this problem together, you will all see that, like, if you've gotten an answer, what you have done correctly is the math. But if you don't feel good about it, it's because you don't see what the physics is yet. And right, that's good. You should want to see the physics. Like, it isn't just raw math. And I want to show you what the physics is, and I will in a second. But I'm going to give you everybody one more minute. Oh, and I'm going to look at this. Okay, so now I'm going to look at this chat. Right, Pythagorean theorem, the 2 lines, yes. So yes, it's a right triangle. And again, I commend everybody who put this stuff into the public chat. I commend you, right. Pythagorean theorem could be used. If you actually try it out, you'll find it would be a right triangle, and I agree with Sarah's. Oh, right, now Sarah's getting it. Okay, that's really good what Sarah put in last. I want to keep my promise and shut up for a second, but Sarah is hitting the nail on the head of what feels insecure or weird about this problem, and she's saying it almost like better than I can. What I'm telling everybody to do is, before I do it for you, I know some of you have done it already, but do the math, do the triangle, get the angle, and then act, and even better than that, don't just do a triangle, try to compose that triangle of arrows rather than just raw sides. If you try to make it of arrows, you'll see more and more why this doesn't seem right, because it'll be hard to put the arrows together into a way that makes sense. It is worth trying because there is a way and it will make sense, but it is hard at first to actually take the arrows seriously and put them together in a way that actually makes sense. And that's part of what Sarah's getting at. But I'll remind you of one thing. Each one of those sides of a triangle, each distance on your page, the length of a side of a triangle on your page represents a speed in real life, in space and time. Like, what we're adding is speeds here, but we're representing those speeds with distances. That's what's interesting and tricky about velocity vectors. They are distances that represent motions. And that may be partly why people are struggling with it. But all right, I'm going to shut up. I'm just going to put the assignment report. So please, again, if you haven't gotten an angle, try to get an angle. If you've gotten the angle, but you're like, I don't know why this is right or what, try to really make that triangle that you have the angle of. Like those of you who rock the angle already, really try to put a tip on each side of that triangle and stand back and look at whether the tips actually make sense or not. When I say make sense, I mean, anytime you see a tip hitting a tail, that's supposed to represent addition. What does it mean to add velocity vectors together? That's sort of the question. I'm going to shut up. I'm really going to shut up. I'm going to shut up. I'm going to put the assignment portal thing in. I might even turn off my video just to prove that, but I might not, because I might not know how. And yes, my nose is perpetually running. There's no question.
I think I have something, but I'm not sure.
Excellent. I'm all, that's awesome. I'm all ears. We're awesome.
So I to make my right triangle, I ended up coming up with like basically an upside down right triangle.
Okay.
So I connected it. I have 2 meters per second going to the east, so that one line.
Like that, is that fair? So
And then I have from that tip, I put the tail of the 5 meters per second.
like this, like something like
Yes,
this.
but mine looks upside down because I ended up going like the actual directions.
Oh, very good. Wait a minute. No, yours is better than I think you're saying. I'm sorry. That's better. You did say that. I mean, in other
Yeah.
words, you're saying like,
That and then going down.
nice, nice. Okay, great. Go. Okay,
Yeah.
awesome. And then go on.
And then you can obviously make a right triangle with that. So I have like a dashed line going down that way.
Awesome.
So you already have 2 meters per second for the first part, and then going down, it's 5 meters per second.
Yes.
So you just have to find what the hypotenuse is. So it's, so you then use the Pythagorean Theorem, which is 2 squared plus 5 squared equals c squared.
Awesome.
And then I got 5.4.
Awesome.
And I did it two different ways just to verify that I got the same answer. But I was looking for the angle that's created between the hypotenuse and the 2 meters per second.
Awesome. Okay.
So at first I tried cosine of the angle equals 2 over 5.4, which then would be arc cos is
Good.
2 divided by 5.4. But then I also tried tangent as well, just to verify.
Nice.
And I ended up getting the same answers. An angle is about 68.2 degrees.
Awesome. Hold on. Yes. I know you did the cosine first, which is great, and then you used the tangent to verify, which is great. And I'm just writing the tangent one down just because ultimately I recommend that, but I totally hear you that you did both, and I think that's great. And do I have it right that you did tangent of the angle equals 5 opposite over adjacent, which is 5 over 2. So the angle is the arc tangent of 5 over 2, right? And you said that's approximately 68, or did you say 68.2?
Yes.
Okay, that's awesome. Okay. And is my diagram more or less like a fair representation of what you're, and I know I left out the cosine, well, I can write that too, but is this more or less what you're saying?
Yes, that's exactly what my diagram looks like on
Awesome,
my page.
awesome. All right, I think this is fantastic, everybody. Again, and I totally thank, and I love that, we went sort of really big on somebody's diagram last time, and it's a different person this time, which is great. And I know it's very tricky to be like, and this time I drew it, she talked it, whatever. We'll just try to do it differently all the time. But I think it does it's super helpful. Let me just say again, anybody who's like willing to like share their thoughts this specifically with everybody, I don't want to keep making it more stressful than this. For some of you, it may not be a big deal at all. I know it is a big deal for me, even though I'm a teacher. Like I feel very naked, like revealing exactly how I think about these things in front of everybody, especially if I think I might be wrong. There's something, but it's super helpful because what I'm going to, everything she just said, like, first of all, it translates to me. I see, and I do agree with her number. I do agree with her answer. And it is the answer that a lot of people put in the chat right away, like fast, and then said something like, I'm not sure about this or something. And even and there is a good reason. There is something weird. I want to just there's actually something weird about this diagram and something weird about this number. The number is right. And it's nothing weird about Sarah or anybody else who did this, but it is. And I love the way there's something super right about this picture, but something that is unsettling that I have to address. And so whenever I do, it's not a criticism of her or anything, but like what's great about this picture is that it's all the correct numbers. It is a right triangle, and it does literally have arrows that are trying to honor reality. Like we know the rain really is going to the east, to the right. And we know, I'm sorry, no, we don't. We know that you, the person, is really going to the right. And we know that the rain really is going down. So that so we're really being precise and observant about this. So then this hypotenuse, according to math, is certainly is 5.4 units long. And by the way, we'll talk about what that means. But if those two other legs are velocities, then that hypotenuse is a velocity. Okay. And let me say that each one of these velocities exists at a moment in time and at a point in space, right? It could be many moments in time and many moments in space, but these arrows represent something that doesn't actually have any length in space, right? Like the 2 doesn't mean that the guy covered 2 meters of distance on the sidewalk. It just means, and you are the guy, it means that at this moment you are going that fast. Like if you were going faster, we would draw a longer arrow, like as we did for the rain. Okay, so that's all fine. So everything Sarah's doing here is right and great. And like, this really does mean that there's some speed that the rain is going at 5.4 meters per second relative to something or someone, not to the ground, but to something. But more to the point, this angle really means something, the 68.2. There's something clearly correct about this angle. And I love that she tried cosine and tangent both to verify. The reason I just I could write them both, but the reason I recommend the tangent, the reason once you trust it, and if you're only doing it once, the reason I always go for tangent is exactly the issue of trust that Sarah's implying. Like I'll always go for tangent because 9 times out of 10, the opposite and the adjacent were the things that were given. And then I inferred the hypotenuse like by using Pythagorean theorem. So just in case I made a mistake. with the hypotenuse, I always feel like the opposite and the adjacent are like the more firm, slightly more firm pieces of knowledge. So I always go for tangent, but whatever it is, she's absolutely right. Sorry.
Professor, I just want to ask something and clarify something. The clarification is that Alyssa was just doing that, not Sarah. I'm Sarah.
Oh,
Just so she doesn't.
I'm so
I don't
sorry.
get credit for something I didn't do.
Sorry, that is so nice of you. Wait, sorry. Thank you. No, you're totally right. I am confused because so wait, both of you are in the, thank you. But the person who, sorry.
Yeah, the person who was helping you draw was Alyssa, not me.
Okay, thank you. I'm sorry. I'm sure
Okay.
that is very, my bad. Thank you.
And the question that I had is because I know you talked about earlier how
I
there's gonna
suck.
be.
Sorry, go on. The question the question you
Yeah,
had.
the question I had earlier, I mean, you mentioned earlier that there's going to be 2 angles in the triangle.
Right.
So, and I see that in my triangle, and I'm not sure which angle we would use for the angle of the umbrella.
Okay.
So that's what I wanted to ask about.
That is a perfect question. So now that's a perfect question and a perfect way to pull me out of what I was just saying. So now for the rest of the time, I'll give credit to that question to Sarah. No, I'm just kidding. No, that is a perfect question. And this is the one flaw in, like, that's what's weird about this picture is at the end of the day, what I do agree with is this angle that we've labeled, and it's also the angle I would solve for. The angle I would solve for this angle because it's the one between the 2 tails. And I would get 68.2 also, like a lot of people have. But to your question that you're asking me, the thing that makes me uncomfortable, the thing that's not complete about this is, wait, why is that the angle of the umbrella? I totally agree with you. Like, how do I see in this picture that that's the way to hold the umbrella? In fact, if I'm taking this picture seriously at all, or if physics means anything, something's crazy here because of course you're right to question this because I don't want to hold my umbrella pointing down like that. If that diagram means anything, it makes it sound like I'm holding the umbrella pointing down. And I totally don't want to do that. And you're right. The key question really is how do you know which angle to choose? And the thing is, the way actually we're looking at this triangle, in a way, it's almost impossible to choose because something is incomplete about this triangle or something. But what we need is a way to know which angle to choose. You are absolutely right. And if we do this whole problem exactly correctly, it will be clear which angle to choose because it'll look like what it should look like. Like if we do this right, and I really mean this question is serious, this is still a compliment to everything Alyssa did. So I have this right now. So Alyssa did this, but Sarah's asking me the question about which angle to choose. Am I, in all seriousness, is that right? Alyssa did talk to me the diagram, but Sarah is asking right now, or do I have it backwards again? I'm sorry.
Yeah, you have it right.
Okay. And I'm not to harp on it, but okay. No, like the diagram is super helpful, but now the one thing I have to extend from it is exactly what Sarah's asking is like, wait a second, we can't be done. The reason a bunch of people wrote me in the chat, like I got 68, but I don't feel good about it, is not that they're criticizing Sarah, is that there's something not good about this. Like, and how do I solve it? How do I fix this? Like, how do I bring this back to what we did the other 2 days? Well, here's the thing. There's according to our belief in vectors, when you place 2 vectors tip to tail, you're adding them. So according to this picture, the 2 is being added to the 5 to get 5.4. Now, what does it mean to add velocities? Like I have to back up for a second. Well, in fact, I'm going to write like, Okay. Here's where here's where I have to come in is that, I mean, this is the non-obvious part, the part that will make everything make sense once you see it, but it is not easy to just like see on one's own. Is that like what I love about Alyssa's triangle is that it was actually composed of arrows, and the triangles mean so. I mean, the arrows mean something. So according to her triangle, like this arrow plus this arrow equals that arrow. Like, and that's true, by the way. That is not a flaw in her diagram. It's true. It's just that it also raises a question, which is, what does it mean for them to be added? Like when we're adding displacement vectors, the thing on the page is just a smaller version of what it actually is that we're talking about in real life. Like when you put an arrow on a page that is a displacement vector, it represents like walking a couple of meters or miles or whatever in the actual space of actual life. So the only difference between the representation and the thing is just size, like the arrow is scaled out, like 1 inch equals 1 mile or something. But now when we draw, and so when you add displacement vectors, like this is to everybody again, and I'm sorry to like be lectury about it, but this is like a whatever. When you add displacement vectors, you actually are picturing the addition of space in reality. Like, what does it mean to add displacement vectors? It means to accumulate space. Like I walked and then I walked more. So I walked a lot. When we add velocity vectors, what the heck are we, like, what does that even mean? Like I could have a baseball fly across my head at 50 miles an hour, and I can have a bowling ball roll along the floor at 20 miles an hour, right now, that could happen. I could add the 50 of the baseball to the 20 of the bowling. I could say like, oh, the baseball's going 50 miles an hour and the bowling ball's going 20 miles an hour. So together they're going 70 miles an hour, but that wouldn't mean anything. Like, what does that mean? That doesn't, like, it doesn't mean that in the room there's now like 70 units of total motion or something. The baseball doesn't benefit in any way from the bowling ball's velocity or vice versa. So put another way, when can we add velocities? What velocities can be added together, and what does it get when we add them? Here's the answer. Remember, every velocity is a relation, okay? We're going to add velocities. We're going to see what Alyssa's diagram like means. And again, it is not wrong, but it reveals something about the world. I'm about to say what it means to add velocities together, like what you get, what the resulting velocity signifies in the physical world. And what it's going to mean, how we're going to know how to add velocities together, is to take super seriously now the fact that any velocity is only meaningful as a relation between two objects. All velocities are relations between two objects. We said this at the beginning of the year, and it's like it's going to come to roost a bit. To be more specific and more mathematically, we're saying all velocities, when you're going to write them down as a v, should really have two subscripts, like a velocity of one thing relative to another. And those subscripts totally dictate how the addition works. That is, I may or may not have, I think I actually have written this for you before, but we've never really used it directly, and we're going to now. Like remember that when I just introduced this problem, I gave you a couple of velocities, two velocities, and I expressed them not just as numbers and not just as directions, but as relations. I said like the velocity of the rain relative to the ground is 5, and the velocity of the U relative to the ground was 2. And I even put subscripts there, like I called one VUG and one VRG or something, right? And just like arrowheads, it's easy to sort of just drop the subscripts and assume that they're like obvious, but what's not obvious is how the subscripts relate to each other. Velocities can be added. Velocities are added very meaningfully only when their velocities measured in two different reference frames. This thing that in English, it's a little too bad that I'm squeezing this into the bottom here. I'll try to write this a different way. I am going to write this a different way in a second. But one big thing I'm saying here is velocities absolutely can be added, just like displacements can. And they're added as vectors, like with Pythagorean triangles and all of that. But the kinds of velocities that we add together, we don't add the velocity of the baseball relative to the room to the velocity of the tennis ball. I'm sorry, we don't add the velocity of the tennis ball relative to the room plus the velocity of the bowling ball relative to the room. Two things measured in the same frame of reference are two objects measured in the same reference. There's nothing communicable about their two velocities. They don't have anything to do with each other. But what you can add is the velocity of a baseball relative to a room with the velocity of the room relative to, say, the ocean, if that room happens to be on a cruise ship. Or in other words, you can add the velocity of a baseball relative to the floor with the velocity of the floor relative to the larger building, if the floor happens to be in an elevator. I'm still sounding vague, but you'll see what I'm really saying in a second. And I think I have, this is Galileo's principle of relativity. Again, in what we call form number 4. I think I may have said this before. I'm just going to remind you. Hold on. What I'm really getting at is why it is that we ever take subways in the first place, right? We take subways because we believe that the velocity of the subway, and I'm saying when it's not a virus, I'm not like making a virus joke, but like normally why we would take transportation, why I would ever get on a subway is because what I really believe is I can have a velocity of 0 relative to the subway. I can chill. While the subway has a velocity of 100 miles an hour relative to New York City. And if my velocity is 0 relative to the subway, but the subway's velocity is 100 relative to New York City, I believe those two velocities add and give me a velocity of 100 relative to New York City. So I get home by doing nothing, right? I mean, in a way, duh. But this is what we believe about velocities, that they do add. You believe you can take the velocity of the subway and add it to you such that without you doing anything, you get home. But why does it add? Because it's two different frames of reference. The velocity of the subway relative to the streets plus the velocity of you relative to the subway gives us the velocity of you relative to the streets. That is that is as fundamental to physics as anything. That is the velocity, and I'm gonna say it one more way, and then I'm gonna write it down the way you've seen before, but now you're gonna see how it relates to this problem, and I won't run out of time, strangely. I'm literally saying, again, the velocity of me relative to Earth plus the velocity of Earth relative to the sun is the velocity of me relative to the sun. Each velocity is independently valid on its own, but they add like that. The Earth bestows its motion on me, if you like, by being different from me. So my velocity relative to Earth is 0. Earth's velocity relative to the sun is 65,000 miles per hour. So my velocity relative to the sun is 65,000 miles per hour. You can't add my velocity to your velocity, but you can add my velocity relative to the Earth plus the Earth's relative to the sun. And what you get, like transitively, is mine relative to the sun. In other words, what we've said, so please write this down, even if whether we've written this before, this is what we call, again, form 4. This is all still the train of thought plan. Everything is coming, it's actually going to make sense of these velocity vectors for us now, I hope, or that's the idea. Form 4 was if you only have one object, like form 4 had 3 cases. This is the 4th form of Galileo's principle of relativity. Again, the first form was laws of physics are the same at all velocities. Second form is you can't do an experiment to measure the absolute velocity of a single object. Third form was all velocities are relations between two objects. There's no velocity. That's a property of one. And I can write those again for anybody at any time. We've written them before. But what I'm writing right now is form number 4, where it gets mathy, where this principle really helps us with math, looking physical problems. This form number 4 has 3 cases. Case 1 is the one object. Sorry, that's supposed to say 1. Case 1, the one object case, the velocity vector. Now, by the way, I'm putting arrows over V's now to signify I'm talking velocity, the vector, like not just speed, but velocity, the vector, the magnitude, the direction, the arrow, the whole package. The velocity of one object relative to itself is always zero, right? Like this is part of what we're saying. Velocity is not a thing that you have. Velocity is something that you relate to something else. So the velocity that any object, A could stand for any object. The velocity of an object to itself is always zero. That's the nature of velocity. But then you got two objects. So you need two objects to understand velocity or measure velocity in any meaningful way. So let's say we have two objects, A and B. And by the way, so if A, B, and C are just like random arbitrary objects, then one object does not have a velocity by itself or relative to itself. It is one object relative to another certainly can have a velocity, but what we've been saying ever since we established this principle is that this velocity that it'll have, this relation, is a symmetric relation. That is, the velocity that I have relative to you necessarily is the negative of the velocity that you have relative to me. Right? Like that's not like, right? If you see me zooming past you at 30 miles an hour to the north, then I see you moving 30 miles an hour to the south, right? And according to physics, we are both right? When I say see, I mean like make measurements, and assuming that both these velocities are constant, then neither one of us is more correct. Velocity is a relation in this way, right? But then the third thing that we said, and someone has, pardon me for saying that's, okay. Oh God, I hope I didn't, okay. But then the third implication of this, and I'm going back to the earlier material to try to make sense of this velocity vector triangle. But so first, what we're saying with velocity is it doesn't mean anything to objects by themselves. It only means something once you have two objects. But if you have two objects, it's sort of straightforward and symmetric. What if you have three objects? That's where velocity addition comes in. We are saying then if you have three objects, A, B, and C, then the velocity of one relative to the third is equal to the velocity of one relative to the second plus the second relative to the third. It seems so obvious once you write it down, but I'm going to keep just talking here. I thank you for everybody's patience. I know like I'm not giving you a chance to do anything yet, but how I'm going to tie this back to our problem now. What I'm saying, this is now the meaning of velocity. So the meaning of velocity addition is this thing. And I'll take it one step further. And is this idea that like you get on a subway, okay, let's try to really. And everything in physics is deceptively simple, right? It is simpler than you think, but it's not easier than you think because it's so simple, right? Like every one of these lines, I think if you just look at it, it looks like, well, yeah, duh. But we still have to use it to unravel that other triangle. And the whole package is definitely not a well duh package, at least not to me. Like what I'm saying now is if you just always bring back the model in your mind of like you and subways and streets or me and subways and streets, right? What we are saying is this is what it means to add velocities. You add velocities from two different but related frames of reference and you get a third of velocity measured with regard to a third. And that's what we're saying. But now we're saying it's easiest to see in the case where one of the velocities is zero. Like it's easiest to see if you're doing nothing standing on a subway while the subway goes 100 miles an hour relative to the streets. We all believe 0 plus 100 equals 100, and that's how you get home. But take it further. We're saying that principle is totally true, really true. We're saying that, like, as you also know, if you were to walk forward on that subway while it's moving, right? Or if you're on an escalator in Columbus Circle, if you're on an escalator that's going 2 miles an hour past the mall, and you're on that escalator in the passing lane walking 3 miles an hour relative to the escalator, right? Like you're passing people on the escalator and you're moving that, you'll see the people in the mall zooming past you that much faster. If the escalator is going 2 miles an hour relative to the mall and you're going 3 miles an hour relative to the escalator, then you're going 5 miles an hour relative to the mall, right? We all know that intuitively. We believe it, but this is what we're saying. We're saying velocities add that way. We don't think that your velocity plus the person next to you, like if you're passing someone on the escalator, you have a velocity and they have a velocity, but you don't add those together to get anything. Like what you do is compare them and subtract them, right? Like if you're going 5 relative to the mall and the person next to you is just standing on that escalator, so they're just going 3 relative to the mall. If you're going 5 relative to the mall and they're going 3 relative to the mall, then in effect, you do a subtraction problem. Look at the last line here on the board. I'm saying, well, then you're saying, oh, your velocity relative to them is your velocity relative to the mall minus their velocity relative to the mall. Like you're going 2 miles an hour faster than they are. That's why you pass them. Like, so this simple addition, like I'm saying this is what addition of velocity means, but if it really means that, then it means I can subtract from both sides and also understand what subtraction means. But this applies even with negative signs, and you know this, especially if you're like I have a 6-year-old and I have a 17-year-old, and both of them have spent a lot of time having fun going up down escalator, right? Like you go to an escalator in the mall that's going down, and if you're a certain type of personality, what's really fun is to like go completely the wrong way on that escalator while your dad is watching and having a heart attack. And if you're like really nerding out, what's really fun to do that some of you may have done or have seen in a cartoon or whatever is you try, like the escalator's coming down, you try to run at like the same speed as the escalator against it, so that anybody watching you from the mall and just seeing your body like in the escalator thing, like you look like the Wild Coyote or something from cartoons, like the legs are moving, your arms are, but you're just standing still, right? You can do that. You can match the downward speed of an escalator with your upward speed so that you get nowhere in a very funny ha-ha or tragic way, because this statement is happening, but with minus signs, right? Like your velocity relative to the escalator is like 5. The escalator relative to the mall is like -5 because you're going up. So what you do relative to the mall is go 0. Like that's how strongly and the last thing I'm saying is we believe this so strongly, we believe that this works even in 2 and 3 and 4 dimensions. Like we believe you can add velocity vectors just like arrows on the page, even with all kinds of angles, even where it wouldn't seem like you. And you don't need, by the way, the whole subway thing, it doesn't matter if you're touching the subway or not, right? Like you could be on the roof of the subway and you could throw a ball off the subway and all this stuff is still true, as long as there's not too much wind screwing it up. It has nothing to do with engines or anything like that. It's just the nature of velocity. So if I go back now to the umbrella, if I'm careful about what these arrows mean, and I know we have limited time, and I still think I still love the answer, but I don't understand, but I'm like with everybody, like, why does the answer mean the answer? Let's go back to the umbrella thing. What we have here is we had a 5 meters per second velocity vector pointing down, which was supposed to be the velocity of the rain relative to the ground, right? And then we had this other velocity vector. It was like 2, like this. And nothing I'm about to say disagrees with any, okay, I'm just taking it farther. We had this other velocity, which was a velocity of like you, the person you, relative to the ground, okay? And we're looking for living now. We're looking for the angle between these two. We're gonna make a right triangle, all that. But now I'm just gonna take exactly what Alyssa did and everybody did, and I'm gonna be super careful about it. Like what she did exactly right is put 2 vectors tip to tail. And that's like the right thing to do when you're adding vectors. But I'm going to look at these vectors and I want to say like, wait, I could put these vectors tip to tail, but then I would be adding these 2 quantities. And actually now that what I've said in English, if I look at these 2 quantities, these are 2 things both being measured with respect to the ground. In fact, it doesn't make sense to directly add them together. Again, it doesn't mean that anything Alyssa was doing was wrong. But if I really take these directions now seriously, it doesn't actually make sense to add like VUG plus VRG like doesn't equal anything. It equals gibberish. It doesn't equal any. But something like VUG plus VG equals something. Like, look, I just remember, the key thing is if you want to add two velocities, they have to be in a certain pattern of reference frames. Like it doesn't matter whether we call them A, B, and C, or in this case, what we have here is here we don't have A, B, and C. We have U, our three objects are U, R, and G. Like U, the person, R, the rain, and G, the ground. It's the same concept, three objects, three frames of reference. But with those three objects, we could say something like, you could put them together any way you want. You could say something like V U G equals V U R plus V R G. That would be a valid statement. Like that would be using the U, R, and G, just like the A, B, and C. I don't care that they're called A, B, and C, but if I follow the pattern of what I was saying, if I follow this, which I have to, this is what this is saying, the kind of velocities you can add are these kinds. And when you do, you get this kind. So if I'm going to follow that pattern, I can't add the velocity of the rain relative to ground with the velocity of U relative to ground. It doesn't mean anything to do that. What I could do, for example, is add the velocity of U relative to the rain plus the rain relative to the ground. That would be one thing. And then I would get the velocity of U relative to the ground. That I could also, just to be clear, like there are options. I could also say something else, like I could say something like velocity of ground relative to U equals velocity of ground relative to rain plus velocity of rain relative to U. I'm trying to emphasize there's many different choices of how to look at this, but there's even more wrong choices. Like there is an arrangement of the three objects that has to be followed in order for it to make sense to actually add velocities. Otherwise, we're subtracting velocities, and all of that is fine, but we have to know what we're doing to make it all make sense. So I'm suggesting here, and I also know we're really running out of time. Yeah. What I'm suggesting here is, I'm going to, for example, do this first option. I'm going to say what's true in English is rain is coming down to the ground. There's rain coming down to the ground. And then, sorry. Hold on. I'm going to try this one. This is, like I said, there's many different options. You can put these things anything way you want as long as it's right. But there's many wrong ways to do it. One right way would be to say RU equals RG plus GU. Again, I'm just following the model from before. I'm saying velocity of me relative to the streets is velocity of me relative to the train plus velocity of train relative to the streets. Right? So I'm following that model. I have all these choices, but here's one choice that makes sense to me because we're looking for what the umbrella should be doing. So one thing that makes sense to me is, oh yeah, what the rain is doing to the umbrella. Like here's like the real point in English is the rain is falling down and I'm standing. If I'm standing there in the rain, it's just falling down because I'm doing the same thing as the ground. When I start walking through the rain, what's really happening is when I start walking into the rain, from my perspective, rain is coming into me, right? Rain is coming down, but it's also coming forward to me because if I'm going forward relative to it, then if I'm going eastward relative to it, then it is going westward relative to me, right? So the faster I walk, the more velocity the rain has horizontally relative to me. If I'm just standing there, rain's just coming down. If I'm going forward, then rain is coming forward to me. And the faster I go, the faster it goes, right? So the faster I go, the more rain is coming to me at an angle and the more I need to hold my umbrella at some kind of angle, like a more and more of a low horizontal angle. But it's all about the rain to me, or who I'm calling you. So how do I figure that out? Rain relative to you must be rain relative to ground plus ground relative to you, right? That's one sensible way to get it. Rain to you, and I know we have like 3 minutes, but I'm saying one way to organize these three velocities that makes sense is to say velocity of rain relative to you, i.e. the angle and the magnitude of the rain coming into your umbrella, will equal the rain relative to ground plus the ground relative to you. Well, rain relative to ground, we know. Rain, and we're almost done, I promise. Rain relative to ground is this thing that, of course, is the 5 meters per second down. Ground relative to you, we don't directly know. I never said ground relative to you. I said what you were doing relative to the ground. But according to relativity, according to the way velocities work and everything I've just said, velocity of you relative to the ground is the exact opposite of velocity of ground relative to you. In other words, if VUG was to the east, then VGU is a vector that also exists, and it goes 2 meters to the west, right? And we're just about done now. Now I'm saying, okay, so I'm taking the same numbers that everybody used, but now I'm actually trying to put physical meaning to them. And I'm saying, given the givens that were given, like the givens that were given were speed of you relative to the ground and speed of rain relative to the ground. But from that, I'm inferring the speed of the ground relative to you. And I'm doing it on purpose. I'm flipping that vector so that now when I put these two vectors tip to tail, as I want to do, as Sarah did, I'm going to put these two vectors tip to tail. And I always draw my horizontal first. And yes, it makes like an upside down looking triangle, just like Sarah. Sorry, just like Alyssa said, sorry. And just like Sarah then asked, okay. But yeah, I'm gonna draw the horizontal first and it's going west now. Sorry. And from its tip, I'm drawing that arrow going down at 5, right? So it's the same triangle geometrically, mathematically, but it's very different now physically. I'm saying now, this hypotenuse, which of course is going to be, just like Alyssa said, approximately 5.4 meters per second. What is that? And we're going to stop in a second. But I'm saying that hypotenuse that everybody got, but didn't like look really like meaningful in the other triangle. And this triangle is starting to make sense, at least to me. What that hypotenuse represents is what the rain's doing. The rain is falling on my head at 5.4 meters per second. Like that rain is hitting me faster now than it would if I just stood still. Because by walking, it still has all the same vertical motion that it ever had, but now it has horizontal motion too, relative to me, because I have horizontal motion relative to it. So now that arrow does look like what's happening. The rain is falling at me, and that's what this is, the velocity of rain relative to me, right? And I would say then this angle right here, which is this angle right here, whichever way you want to look at it, the angle between the tails, which is the angle, so theta is between the tails and measured, and I know we're just about done, but we really are ending at a perfect place, and I really do. I mean, I'm actually surprised we got this far, to tell you. I'm pleasantly surprised. Like, notice that if I draw the triangle this way, so her triangle was already intelligently flipped. I've kind of flipped it even more now by using Galileo. Now my triangle, the angle that is between the tails is the angle measured from the horizontal, which means I know I did something right that actually makes sense. That's what you always want. You want an angle between the tails to be from the horizontal, because now that angle, which is the same answer everybody got, right? But that angle, what it's really saying is, that's the angle that the rain is coming down at me. So that's the angle I hold my umbrella. Like that angle up there in the triangle literally is the angle that the rain is making from the horizontal. And the angle down here, it's, you know, whichever way, it's the same angle. The alternate interior angle down here is literally the angle of the umbrella. Which you can't, it's hard to see in the other triangle why that's even true. But but I think everybody did great. I will put the other assignment portal in a moment, but I did put one in, I think, or I'll finish putting in. I'll put them both in while the other class is coming in. I'm going to sign off now because the other class is about to come in, but I hope. So the answer is 68. That is right. It is. And 5.4 meters per second is the speed at which the rain is falling relative to you and your umbrella. And if you understand that, then you've just added two velocity vectors together in a meaningful way, but we'll keep. So I hope that's clarifying. I'm saying goodbye. Could someone just say goodbye to acknowledge that we're saying goodbye? Or if it's okay, I'm saying goodbye. I think it worked out. Oh, right now I'm actually worried that I can't hear. Could someone just say goodbye or something just to acknowledge that you've been here? Oh, okay, thank you. Okay, all right, okay, bye.